All right, what's up, YouTube? Today, let's go over the math behind supervised learning, and I was a subset of machine learning. Okay. Um, Quick outline. So I want to talk about the big picture a little bit, although I think the big picture is maybe obvious, and I think there's better intuition, high level building videos. This is more about like the math and pulling together all the different types of math I feel like are just kind of not explained in as much detail as I would have wanted when I was trying to learn this stuff. So that's what I want to try and focus on. So a little bit about like gradient descent, and then we're going to talk about all these different types of networks, essentially starting from linear regression to an MLP, which is a type of neural network. And each of these networks basically add one new layer of complexity, and then we're just gonna keep adding on new types of complexity until we make our way to a neural network. And I don't think this through line is really taught. At least I haven't really seen it so explicitly, and I think it's kind of helpful. So that's what I'm also gonna try and focus on. Okay, but the high level is supervised learning, and the whole point of supervised learning is that you have a data set that has X and Y. So you have the inputs to some function, and then you've also gone out and you've measured labels. So labeled data. So basically, the goal is to create some function where you input X and output some prediction Y hat. And you want to do that really well. And in order to learn how to do that really well, you need a data set to learn from. So the whole point of supervised learning is that you have this data set, and then we're going to go learn how to map X to Y. That is exactly what supervised learning is doing. You're mapping X to Y in the training phase of things. And then you can go out and take your final product and then just take new X's and hopefully that they perform well. But the point is we're learning that you're learning from this data set with labeled data, which means you have the output. You have a bunch of examples of like correct outputs. Okay, so at a high level, how you learn things is what's called gradient descent. And it's not going to be quite clear yet, but first of all, if we have some prediction, so this is the notation we're going to have for a prediction with input X. So if we have some prediction, Y hat, we need to see how good is Y hat. Is it a good prediction? Is it a bad prediction? Don't know. So we need a math way to do that. And so the notation for that is called the loss. So you have a prediction Y, and then you want to compare it with Y, the true Y. And that is like for one Y hat. And then the cost is with this notation. So the average loss of all of your Y hats. So for all of your predictions, what is the average? How do you perform? And so the reason this takes in theta is because theta is the parameters, like you see here. And we'll see kind of what that means, but the parameters are input because we're going to be tweaking the parameters when we're learning, and we're going to output the lowest average loss possible. So this is the loss, and this is the cost. So the loss is saying like how bad is our prediction Y hat, and we're going to find the lowest average loss over all of our Y hats. And so the reason you have many Y hats is because you're doing this over your whole data set. There's a better way to draw this, I think. Let's see. So your j of theta is created by okay, so let's see. We have a data set, and then we also have our prediction. And then we want to use the data set and our predictions to generate some cost. And that's J. Does that make sense? So you're going to run this prediction over the whole data set, and that gives you your cost. And then that's how you know how to update. So then we go, like, how do we update the parameters? So this cost function is just a function, right? So when you want to minimize a function, you find the lowest point on the graph. But since these are complicated functions, you may not be able to take the derivatives at equals 0. So you do something like gradient descent, which kind of looks like this. So you're basically stepping in the direction of the gradient. So you're going to run over your whole data set in order to calculate the cost. So yeah, so your cost function is dependent on essentially your whole data set, which means you have to find the step for that function that goes to the lowest point. Okay, so now let's talk about more specifically how these functions, how do you predict something, and then how do you find the gradient of the cost function so that you can update the parameters. Okay, first let's start with linear regression, which is kind of like a warm-up, I think, because now it's really just about learning the notation. Okay, so let's see. So in any of these types of networks, we want to define how to define a prediction. We want to define how good is one prediction, and then we want to define how good were all of our predictions, and then we want to find the gradient of that cost, so that we can update our parameters and then have a new prediction function. So then we do this cycle a bunch of times and make our parameters better. I think we'll have more clarity on what that means in a second, so don't get lost there. Now let's just go through linear regression and see how it works. Okay, so for linear regression, this prediction is just right where these are the parameters. So different parameters give you different types of lines that you can draw. So you want to find the line that minimizes the loss. And so now we need to find the loss. So all these networks kind of feel like they pull the loss, like how to define the loss, like out of nowhere. They all have like a little bit of intuition, but there's really only two types of loss functions that are relevant here. So once you see how they work, it's like, okay, it starts to be more familiar, and then it gets easier. And that's one thing that I think is really important, is like we only add like a little bit of complexity every time. So there's gonna be a lot of new things here, but it's gonna get a little, like, not too bad as we keep moving. Assuming we can get past this first one. Okay. So how to define how good one prediction is? Well, we might as well just find the distance, right? So here's our data set, and then this function is just a line, maybe in many dimensions, but in one dimension it's just a line. So we might as well talk about the distance of the prediction and to see how good we are. Okay. So it's really just the squared distance. And then the cost is always just the average over the whole data set. Okay. So now the goal is to find the gradient of this. And to do that, let's just start with one parameter. So first, let's put in, so y hat equals h of 0 of x, and h of 0 of x equals this. And so we're taking the derivative with respect to some parameter, let's just say some w, great. Okay, so this just becomes that, okay, so that was probably confusing initially, and so let's break it down a little bit, but I also want to pick up the pace just a little. Okay, so part of the learning curve here is just remembering stuff from calculus and multivariate calculus, and then applying that to the weird notation. And you have sums that are distracting, and you have all of these letters, and it gets distracting. But this here, I promise you, is just simple calculus. So basically what happened is we're taking respect to wi. So you can imagine this as w1, x1, w2, plus w2, x2, etc. And so if I is equal to 2, then the derivative of this is 0, and the derivative of this is x2. So that's where this comes from. And this is just repackaging. So that was just the chain rule and then the repackaging this. Okay. So that is the derivative of j with respect to wi. And so we can do the same thing for b, but it's just going to be a 1 in that spot. And yeah, okay, so like this. Okay, so that means our gradient is really just a vector of like all of these terms. So now we know what direction to go to. So when you do gradient descent, you initialize your parameters to anywhere randomly. It doesn't matter. And so you want to find the direction to go and minimize. So j, So j over here is just this function, right? And so you can theoretically graph it and say, what w's and b's do I want to use so that the j is low as possible? And so the gradient, by definition, is the direction of steepest ascent. So we're just going to go update our parameters in the negative direction. So we started at some parameters, and then we're going to update them to be in the opposite. So the gradient would be pointing this way. So now we're going to point them in the opposite direction and take a step. That much. So the gradient is a direction, right? In many dimensions, the gradient is a direction of steepest ascent. And then we're going to go this many steps. This is just a constant. Okay, so and then we're going to do that a bunch of times, because as soon as we update the parameters, then we're at a new spot on this graph, and the gradient is now different. So we need to recalculate that gradient based on the new spot, and then we go again in one step, and then we go again, and then we go again, and then we go again, and we're going to find our way towards the bottom, hopefully. Okay, so that is the flow, right? We have some cost function, we have some parameters, and then we have some cost function that depends on those parameters. And so we find the gradient of that cost function, which will definitely use our prediction function, because we're seeing how close is our prediction to the real value. And once we have the gradient of that cost function, then we take a step in the negative of that direction, so that we're going down. And we do that a bunch of times. And so every time you do that, your parameters will be better. And by better, it means the cost function j is lower. Okay, so that is the idea behind gradient descent. And basically why you have this whole workflow where you collect a data set, and then you have some model. Right now, all we know is linear regression. So we have the data set, we have our model, which is a way of going from x to y. And then we define a cost function, which is a way of comparing our prediction with the real value. And now that we have a way of comparing, we have a way of measuring how good those predictions are on average. And all we have is our data set, so we do an average over the whole data set. And that is what our cost function is, and we want to minimize the cost function. Okay, great. So you can see, and it's the same workflow across all of these models. So we're going to have our data, we're going to have a way to make a prediction, we're going to have a way to see how good a prediction is, and then we're going to have a way of minimizing the error, or making those predictions as best as possible. Okay, good. So that is linear regression and the gradient descent workflow. So now let's do logistic regression, which is just one more piece of math, like one more function we add on here. And now we're going to step and start using vectors, because one thing that is super hard is vectorization. And no one really teaches you that. You just have to see it enough times that you get it, which is an annoying thing, to be honest. Okay, cool. So here I've labeled some things. Before, this was very simple. So these letters might be confusing to start. Okay. So we're going to build up with these pictures. So now instead of x1, x2, w1, w2, I've put them in vectors. But that's okay, because we already know this is great, right? So this was what we had for linear regression. And that's just a way to predict some number. And so then this is our old value, and now we call it z. And we're going to use this whole time, so this is not random. Okay, so we have our linear regression from last time, and now we're going to add one more step, and that is this sigmoid function. So this sigmoid function is something that looks like this, and the graph of it actually looks like ooh. Oh gosh, that's a bad way to draw it, but you should look it up. That is a sigmoid function, and we call this a. And that's the only thing. So that also equals our prediction. So logistic regression is linear regression, except we take the output of the linear regression and put it in the sigmoid function. So we're just one more step. And that one more step actually does some interesting things. Okay. And that is our prediction. Okay, great. So now we've defined how to predict y hat, how to make a prediction given the input x. And that is the only change that we have before. So now I'll go back and add the labels. So all of these three things come together to make z. And then we use the sigmoid to make a. And then that's the same as our prediction. And then we're going to have the loss. Okay, so now we got to get to the loss. How do we compare how good y hat is with y? And so this is going to seem a little random. And I'm not sure we have time to talk about this. Okay, so yeah, so that is how we compare how good y hat is with y. And basically where this comes from is, I don't know, I'll do a side quest on this later, but I don't think we have time. But basically, yeah, honestly, it doesn't matter, realistically. Like, all you need to know is that this is the way that you compare these things. And once you have a way to compare these things, then you'll have a way to measure the error across the whole data set. And then that's what we know we want to minimize. Okay. So then, cool. Okay, so that's that. And so let's see. Where are my notes? Where are my notes? Where are my notes? Okay. Awesome. Okay. So now we need to find the gradient of this. So first of all, let's start with okay. So this is a lot more notation, but it's going to be useful later, I promise. All right. So this is the chain rule, and because we want to know this, and this turns out to be y hat minus y, which is an awesome conclusion. And the algebra doesn't really matter. But now that we have this, then we can easily find, right, so the gradient of j every time is going to look exactly like the parameters because it's an update to the parameters. So it's really just about finding stuff like this every time. So you want to be able to find this so you know how to update that parameter. And that makes it nice because we can do stuff like that. And that's great because then we can do that. And oops. Yes. Okay. So and this should look very similar because this is the same thing from linear regression, which is pretty crazy. So what this is saying is that the updates to the parameters is actually the exact same, except the way to calculate this prediction is different. And yeah. Okay. So now let's go here and we're going to do logistic regression with multiple outputs, multiple classes. So let's see. All right. So fun fact, this is also the same gradient with just some extra packaging in the prediction. So I'll show you how we get there. So here, now we're talking about matrices, and we've graduated from scalars to vectors to matrices. Okay, so Z equals W X plus B, except this is a matrix now, and this is a vector. All right, so W is, let's see, K, is it n by K, or K is the number of clauses? Oh, fuck. Yeah, I think it's that. Okay. So then we have A equals this Z. But now Z is also a vector, right? So the sigmoid is going across the vectors. And now... Oh, shoot. That is not true. We're doing softmax. Okay. So we have all of our Z's, but the new thing here is what's called softmax. And softmax is a function that looks like this. And it's basically like sigmoid, but for many things. Oh god. What do I do? Okay, so it's basically like sigmoid, but for many different outputs. So here the output was just one number, and now the output is K numbers, right? And so how does that really make sense? So before, we were predicting a number between 0 and 1, because it was a prediction for one thing, like is this house good or not? And now we're predicting a whole vector of numbers. And that changes things. But it doesn't change the gradients somehow. Right, okay. So now our cost function equals this guy. And this is kind of confusing, okay? So here we go. This should look very similar, though, to what we just did with logistic regression. Look exactly like this. Except instead of two things, we're predicting K things. So that is where that comes from. And it can only be 0 or 1, so this could be like yi. So so this number is either 0 or 1, and this is some probability. Okay, awesome. And so now we got stuff like this, and we can get the same thing like this. Awesome. Okay. And keep in mind, these look the same, but they're not exactly the same because this is calculated differently. All of them have different types of predictions and different data types. But at least we know how to update the weights so that we can make our predictions better. Okay, so now we've expanded to multi-class prediction, and now we're going to expand the other direction horizontally to see how to chain logistic regressions together. Okay, so here, this is now the place where the model architecture gets a little more complicated. So writing down this gets a little bit more complicated. But in this one, it's not too bad. Okay, so first, we have Z1, and which is just the same thing we had before, WX plus B. Yeah, and we're going to go back to vector land now. And then we have A1 equals sigmoid of Z1. So we're back with sigmoids as well. And we're going to put it all together into the neural network after this. And then instead of that being it, so this is just one logistic regression. And then we're going to do it again. So now Z2 equals, this is W2. So just a new set of weights. Awesome. That's a 2. Awesome. Okay, great. So now we just chain 2 logistic regressions together. And then the final output, this is why we've been having this notation around this whole time, because we want to know what the final output is. And that's just A2. Okay, awesome. Okay, so great. So that is when we put in an X, that's what we get. That's our prediction. That's how we get a prediction, is by doing these 4 equations. And so now we want to calculate the gradients, but this time it's not just one simple thing. We have multiple sets of parameters in multiple places. So it gets a little bit more complicated. But that is kind of where the new complexity comes from. And once we do this, we can do neural networks. Okay, so here, so the goal is we want W1, we want W2, and we want B1 and B2. So we want them for all of these. And there is generic equations that we'll get to in neural networks that you can calculate for like arbitrary ones, but right now we want to just do it nice and simple. Okay, so first things first, this is our trusty reliable right here. We know that can be true because that has been true this whole time. Okay, so that's with respect to this. I should say the loss. So the loss here is the same thing that we've had the whole time. Or in original logistic regression, right? Because no matter how horizontal we get, how deep we go, comparing y hat is still the exact same because we end up in logistic regressions, so the y hat is exactly the same. So we might as well compare y hat to y in the same way we've already been doing. So J0 is the same, which means this is the same because we haven't really gone deeper than we have before. So actually all of the things, so the first one are like kind of exactly the same. Right, the closest to the loss is all exactly the same as we had before. Yeah. Something like that. Great. So then now the question is, how do we go deeper to get the gradients for these? Like we already have these two. That was pretty easy. That's just original logistic regression. But now we need to go one more deep. And to do that, that's what we want. So to do that, we can use the chain rule and basically say that is equal to this one, which we already know, with Z2 and respect to W. Oops, we've already done that. I see. Okay, so let's hold off on this. In order to do that, we need to get here. And then we can go out. Okay, so we need to get that first. So that's J, Z2, and then Z2, A2, no, A1. Yeah. Okay, that should be one up there. Yeah, A1. And now we can go A1, Z1. Yep. And then Z1, W1. Okay, so this is the chain rule among these functions so that this will all cancel out. Bang, 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 and give us what we want. And then we can generalize what we just did, actually, for neural networks. Combine that with softmax, and that's kind of all it is. Okay, boom. So then this comes out to be, I think it's like 1 over M. Okay, let's see. This is the general form. Okay, well, let's just do it. So J, DJ, DZ. We already have, so that's this. And then DZ2, DA1. Oh, shit. Okay, sorry. Yes. So you can see that this becomes the input to that. The output of that becomes input of the Z. Great, so DZ2, DA1 is like W something. I think there's a transpose, but we'll see. You have to make sure the shapes line up, which is another hard thing to do. A and Z. Right, so that's like that guy. And then DZ, DW. Oh, well. Okay, we don't need that right now. Okay. Got it. Okay, so does that make sense? So we just did the chain rule there, and then to get the one with respect to W, you take that with this with respect to W, which is just like xj. And so this is not like 100% accurate. You have to match the shapes. But this is a speed run, as always. Okay. So now we're on neural networks. So now we have learned vector notation. We've learned matrix notation. We have learned logistic regression, which is just linear regression with the sigmoid, and then we learned softmax, which is just logistic regression, but you have multiple outputs, meaning you have a new type of sigmoid, which is softmax, and then you have a new type of loss, which is cross entropy, instead of binary cross entropy. And now we can combine all of that. So we add one more layer horizontally to the softmax, and that gives us a multi-layer perceptron, which is the OG of neural networks. Okay. So now we go back to our matrix notation, and we do a very similar process to what we just did, and then we'll end up at the general forms for the gradients. And then because we have those general forms, we can go arbitrarily deep, and then the gradient descent will be somewhat efficient, because what we ended up doing was backpropagation, and backpropagation is just a more efficient way of calculating the gradients, and we are going to calculate the gradients in a way that is efficient, because that's the only way we need to do it. Okay. Oh, all right. Wonderful. Okay. So we have W1 X B1. So this is this. And then we have great sigmoid of that. So now we just did linear regression, but this is element wise, right? So now we get to A. And then these are all like individual probabilities and whatnot. Okay. So now we do the same thing where we have Z2. So this was just like one logistic regression. That's it. This is one logistic regression as normal. Now we have Z2, which equals W2. Not going to make the same mistake. B2. Okay. And that's A2. And now, instead of doing a sigmoid, we do the softmax, because this is our output. And they are kind of the same thing. If you're only predicting two classes, then it's kind of the same thing. But it's still confusing. Okay, so now this is the same thing as the softmax from before. And then that is our prediction. And so now we use the same loss as the softmax. So anytime you're using softmax, you're going to use the same loss. Anytime you're using sigmoid in the output, you're going to use the same loss. Anytime you're using linear regression, you're going to use the same loss. So those are the only losses that are relevant here. And once you see them, you can reapply them, and because you can reapply them, you know the gradients. Okay, so we have the same loss, and so now we could just calculate respect to W2, W1, B1, B2, right? We could just do that again. That would give you basically the same answer, except with the softmax changes a little bit. But now the whole point here is that what if we added two more logistic regressions in here? We chain two more in. How can we calculate those gradients efficiently? And so there's a general equations that we can use actually instead. So here's what it is. So we have dj dz of the last layer boom. And so this is always equal to y hat minus y. I'm pretty sure. Maybe not always, but in these equations with the softmax, it is. Okay. So that is the what's called error in the last layer. And so then now let's try and find the error in some arbitrary layer. Lowercase l. Okay. So then so let's look here. So we actually had it very close before, which is this. So here we had the same thing, but instead of the Z2, we just are going to do for like an arbitrary layer ahead of where we are. So in that case, it's the last layer, which is where the y hat minus y came from. But in terms of an arbitrary layer, you can just leave it like that. All right, so that is what we have. And then, so we know A with respect to Z is always like the sigmoid prime unless it's in the last layer. So that's chill. And that's multiplied by Z respect to A. So that's like some W. And then J respect to Z is just the error from earlier, which we don't necessarily know. We're going to cache it as we go. Boom. So that's how you get the derivative. And then you do that times derivative Z respect to W. That's how you get the W, or you do Z respect to B. And that's what you do on every layer to get the weights. So that is how you calculate the gradients. And that is how you make the minimize the cost. And that is how you do supervised learning up to neural networks. That is not my best work. And I'll have to remake this video. Sad.